Hey everyone. So today we're going to be taking a look at section 5.6, which is over optimization. And what we try to do in this section is we try to find the optimal solution to real world problems. I find this to be one of the coolest sections in calculus because the problems that are proposed in this section are easy enough for anyone to understand, but they require calculus to solve. So this is when people ask like, well, when could I use calculus in the real world? You could propose this question to them. They'll sit there and think about it and be like, I understand exactly what's being asked here, but I do not know how to find the answer. And they'd be like, calculus gives us the answer to these types of questions. So here in example one, we're actually not going to solve this problem. The next two slides will be the solution. And that way, if you need to see how to do this, you can always refer back to the slides or the notes that will be attached. But this will give you an example of what we're looking at here. So it says that a homeowner has $320 to spend on building a fence in a rectangular garden. They say that three sides of the fence will be constructed with wire fencing, which is going to cost them $2 per linear foot. And the fourth side will be constructed with a wooden fence, which will cost $6 per linear foot. And it says find the dimensions and the area of the largest garden that can be enclosed with $320 worth of fencing. So if you take a look at the picture, they show us exactly what's going on. We have an X by Y rectangular garden where three of the sides cost $2 per linear foot and the fourth side costs $6 per linear foot. So the idea is that we're trying to maximize the area, which would be X times Y in this case, while keeping our cost at $320. Which means that we probably want to reduce how much of the wooden fence we're going to be using, but at the same time, we don't want to reduce it by so much because we're still trying to maximize area. So in order to set up our problem, there are a couple things that we need to take a look at. So the first thing that we want to do is we want to come up with an equation that relates the dimensions of the fence. So we know that the area is X times Y. So that's where we get area equals X times Y. We don't really know what X or Y are yet, but we know that that is the area. We also know that we should be using all $320. I mean, the idea is if I had money left over, that's more money I could have spent on fencing, increasing the area. So I'm going to use all of my money. And if I want to calculate the cost, I can take a look at this equation. I knew the dimensions were X times Y, and the costs were 6X for the wood, 2X for the chain link fence, 2Y for chain link fence, and 2Y for chain link fence. So C is 2Y plus 2X plus 2Y plus 6X, or 8X plus 4Y. We also know that we have $320 to spend, so I can plug that in for C. So this gives us two equations. We're trying to maximize the area, which is X times Y, and we're subject to the restriction that 8X plus 4Y equals 320. So what we can do is we can solve for one of these two variables, X or Y. So if I take my equation 8X plus 4Y equals 320, I'm going to solve for Y in this case. You could absolutely go ahead and solve for X. Both of those will be fine. I get that Y equals 80 minus 2X. So on our last slide, we solved for Y. We got Y equals 80 minus 2X. And this came from our cost function. We are going to plug this into the area. We know that area is X times Y, and we know that Y is 80 minus 2X. So I could say that the area is equal to 80X minus 2X squared. Now, why would I want to do this? It's because I can actually, if we go back to our max and min section, I can find the maximum value of X in this case, which would give me the most optimal value for X, because I'm maximizing my area. So to get started, we do need to look over a few restraints. We know that X and Y are going to be real lengths. Because these are dimensions, we can't have a a length of a fence be negative? So we know that x is going to be strictly positive. We also know that y has to be strictly positive. So if we wanted to solve it this way, I can actually find a domain range for x. I know that x has to be non-negative, so x is going to be greater than 0. I also know that y is going to be greater than 0, and I know y in terms of x, so I can find out that x is at most 40. The minimum would be a 0, and we definitely know that's not a solution. So the domain for x has to be from 0 to 40. So now I'm going to try to find critical values for a. I know that the area is 80x minus 2x squared. So if I take the derivative, a prime, I get 80 minus 4x, where x equals 20 is a critical point. Now, because I'm trying to find the maximum area, the 3 points that I'm going to have to take a look at are a of 0, or a prime of 0, a of 20, oh yeah, not a prime, just a of 0, a of 20, and a of 40, to figure out which one of these gives me the maximum area. We look at the first derivative to find our critical values, but then we plug into the original function to find the actual value. So if we plug in, we are going to see that we get a maximum area of 800 when x equals 20. If I plugged in 0, I would get an area of 0, and I believe if I plug in 40, I'm going to get an area of 0, meaning that 20 is going to be my max. At x equals 20, I get an area of 800. And now what's nice here is I also know the relationship between x and y. Y is 80 minus 2x, and if x is 20, then my y has to be 40. And that's what we're seeing below. We get a maximum area of 800 when x equals 20 and y equals 40. So that would be our answer to the question. We're going to build a fence that's 20 by 40, where the wood inside is the 20, and the maximum area we'll get is 800. So these examples are a little trickier than anything that we've dealt with so far, because we're trying to apply our calculus to the real world. But the more you do these, the easier they get. And I really like these problems because we get concrete answers. These are answers that the average person will understand when you give it to them. So some strategies for solving optimization problems. The first thing that we want to do is we want to introduce variables and look for relationships among the variables. This is kind of like when we were saying, well, our dimensions are going to be x and y, so our area is x times y. The next thing that we want to do is we want to find critical values for the function that we're trying to maximize or minimize. And then we want to kind of do what we did in the absolute max, absolute min section, where we do need to find the critical values and the endpoints of our domain. And we plug in to see which one is the maximum or minimum. And that's how we would solve our problem. So let's take a look at a couple more examples. There really aren't new notes for this section. It's all application. So hopefully this is going to start tying everything that we've learned so far together. So example 2 is a continuation of example 1. So that's why everything's looking the same here. It says that the homeowner judges that an area of 800 square feet for the garden is too small and decides to increase the area to 1,250 square feet. I'm asking, what is the minimum cost of building a fence that encloses a garden of 1,250 square feet? They're asking, what are the dimensions of the garden? And they're saying, assume that the cost of the fencing remains unchanged. So this problem is similar to part 1, but definitely different. So before they were saying that I have a budget of $320, what's the biggest yard that I can make? Now they're saying that I need a yard of 1,250 square feet. What is the minimum cost that it will take to make that fence? So similar, but definitely different. Because before we were trying to maximize area, we didn't know what the area was. Now we know what the area is, but we're trying to minimize our cost. So just like in example one, I actually have this problem already worked out for us. And we're going to just go by slide to look at what we're doing to solve this problem. So again, when we take a look at example two, a lot of the stuff from example one is going to carry over. Our cost function remains the same. We are trying to minimize the cost, which is 8x plus 4y, just like in example one. And our restraint is that x times y, or our area, is going to be 1,250. So also just like in example one, I need to solve for one of my variables. So if I know that x times y is 1,250, that means that I could solve for y. And again, you could solve for x here. It really doesn't matter how you go about it. But I get that y is 1,250 divided by x. So if I take that and plug it into my cost function, which was the 8x plus 4y, I get that the cost equals 8x plus 4 times 1,250 divided by x. And when I solve this problem, I can go ahead and distribute the 4. So I'm going to get that the cost is 8x plus 5,000 divided by x, and x has to be greater than 0. Because I have an x in the denominator, and I'm going to have to take a derivative, I'm bringing it up to the numerator and making it a negative exponent. If you want to keep it in the denominator, that's fine. You're just going to use the quotient rule, and I find that power rule is going to be a lot faster. So if we take the derivative of our cost, that's going to give us 8 minus 5,000 x to the negative 2. Converting that negative 2 back into a positive, we get that c prime of x is 8 minus 5,000 over x squared. Solving for x squared, we're going to get that x is plus or minus 25. And if you're not seeing that, let's just go ahead and do that calculation here. What I'm going to do is I'm going to move that 5,000 over x squared to the other side, so I'll get 8 equals 5,000 over x squared. Then multiply both sides by x squared. So I get 8x squared equals 5,000. Divide both sides by 8. And that should give me 225. I'm going to double check with my calculator real quick. 5,000 divided by 8 is 625. Yeah, 625. So that when I take the square root, I get x is plus or minus 25. So that's how they're getting this answer here. But we also know that x has to be positive, so that gets rid of our negative root here, and we know that x is equals 25 is a critical value. So now using a sign chart, we can determine what our critical points are for a minimum. And it's going to come out to be that x is 25 will be the minimum. Yeah, we didn't go through the domain in this problem, but we know that x has to be at least 0 and y has to be at least 0. But if we plug in the values that make x and y 0, then our area is stuck being 0. So 25 is our only candidate. And when we plug in 25, we get that our cost is $400. So if we solve for y, using 1,250 divided by x, we get that y equals 50. So the minimum cost of enclosing a 1,250 square foot garden is $400, and the dimensions will be 25 feet by 50 feet, where the 25-foot side is the side with the wooden fencing. And I think there's a typo here that should say the minimum cost. On this slide, we're going to be taking a look at example 3. And example 3 is our first problem that's not already worked out for us. So we're going to work this one out together. So it says that an office supply company sells X permanent markers per year at P per marker, or P dollars per marker. The price demand equation for these markers is P equals 10 minus 0.001X. They're asking what price should the company charge for the markers to maximize revenue? And then they also ask what is the maximum revenue? So they remind us that revenue is equal to price times demand. So to get started, we want to get our revenue equation. So R of X, the price, they tell us here, P is 10 minus 0.001X. So we're going to get it's going to be 10 minus 0.001X. And the demand is X. We know that because they call this the price-demand equation, meaning that P is our price, X is our demand. So let's go ahead and multiply this out. We're going to get the revenue is 10x minus 0.001x squared. So we want to maximize this. Now we do have restraints of we need our price to be greater than 0 or we're not making any money. And we also need our demand to be greater than 0 or we're not making money. But those values in the end should give us a revenue of 0. That would be like if we wanted to be a nonprofit. I guess we're not really considering cost in this problem. But either way, we can find the domain of X. We know that X has to be greater than 0. We need there to be a demand. And if we want to find the higher end, what we would do is we would say that we want our price to be 0. When is our demand so high that price is 0? We're going to get 0 equals 10 minus 0.001x. So move that over, we're going to get 0.001x equals 10. So if we divide both sides by 0.001, 10 divided by 0.001, we get x equals 10,000. So this is our domain for x. But we also want to find, well, what is our critical value? So to find critical values, we take r prime. So the derivative of 10x is 10, and the derivative of 0.001x squared is going to be 0.002x. We need to set this equal to 0. And when we do that, we're going to get 0.002x equals 10. So x is going to be 5,000. So the points that we need to test r of 0. We need to test r of 5,000. And we need to test r of 10,000. So if I plug in 0 for revenue, I get 0. If I plug in 0 or 10,000 for x, I'm going to get 0. So 5,000 has to be my my max, which let's take a look here. It's going to be 10 times 5,000 minus 0.001 times 5,000 squared. And when I plug that in, I'm getting 25,000. So my revenue is going to be 25,000. And what else were they asking for? They were asking for the price. So to find the price, I need to plug into my price equation here. P equals 10 minus 0.001x. And when I do that, my price is $5. So I'm going to sell these pens for $5 a pen. And my revenue is going to be $25,000. So here in example 4, we're going to do a continuation of example 3. So it says that this time we want to consider what the cost of manufacturing is. It says that the cost of manufacturing X pens is 5,000 plus 2X. So they're asking what is the company's maximum profit and what should the company charge for each marker and how many markers should be produced. So they say that the profit is P of X equals R of X minus C of X. So profit is revenue minus cost. And just a point of clarity here, we kind of have two P's floating around. We had our price, where P was 10 minus 0.001x. But we also have our profit. So normally I would say that one is like a lowercase p and the other one's a capital P, but my handwriting's so bad that it's hard to tell the difference. So when we say P of X, we're talking about profit. And if I just talk about P, I'm talking about price. I'll try to be as clear as possible. So yeah, in our last problem, we had the revenue. We said that our revenue was 10x minus 0.001x squared. So if I want to find my profit, I'm going to do R of x minus C of x. And when I do that, I get my profit, P of x. It will be negative 0.001x squared plus 8x minus 5,000. So to find the optimization, I'm going to have to take the derivative of profit. So P prime of x. That's going to give us negative 0.002x plus 8. And we need to set this equal to 0. So this will give us 0.002x equals 8. So x is going to be 4,000. So we're going to need to manufacture 4,000 pens. How much profit will that give us? What is P of 4,000? Well, if I plug 4,000 into the profit equation, I'm going to get $11,000. So that's how much money we bring in after we take out the cost. And then what is the price for the pens? Well, we're going to use our price equation again. This time x is 4,000, and I get the price is $6 per pen. So let's take a look at a few example problems. For number one, it says find two numbers whose sum is 15 and whose product is a maximum. So two numbers, when I add them together, I get 15, but when I multiply them together, it is a maximum. So a little stipulation here, they're saying the two numbers, but they're not saying two distinct numbers. And we're going to see that in our answer. The numbers are allowed to be the same number. So two numbers whose sum is 15. Well, let's say that number one is x and number two is y. X plus y is 15, and we're trying to maximize x times y. So what I'm going to do is I'm going to solve for one of my variables. It doesn't matter if we solve for x or if we solve for y, so I'll solve for y. So y equals 15 minus x. And I'm going to take that in and plug it into what I'm trying to maximize. So I'm trying to maximize x times y, so this is going to be x times 15 minus x. So that means I'm really trying to maximize 15x minus x squared. So if I take the derivative, I'll get 15 minus 2x, set it equal to 0 to find critical values. I'm going to get x equals 7.5, which means that y is also going to be 7.5. If you want to check the answer, 7.5 plus 7.5 is 15, so that works. And then 7.5 times 7.5 is going to be our maximum product. Let's take a look here. 7.5 times 7.5. This means the product is going to be 56.25. And that will be our maximum product. If we were working with two distinct numbers, the problem is like I could use something like 7.4999999 and 7.500001. So if I said that we're only going to work with whole numbers, so I need two whole numbers whose product is a maximum, this would change the question a little bit. I'd have to do something like x and y, but x and y have to be different numbers. It would be a totally different problem, so we're not even going to worry about that. So let's take a look at number 2. It says find two numbers whose sum is 21 and whose product is a maximum. So same kind of situation here, two numbers, so x plus y, and they equal 21. And then we're trying to maximize x times y. So let's go ahead and solve for one of the variables. Y is 21 minus x, which means that we're trying to maximize x times 21 minus x, which means we are maximizing 21x minus x squared. So go ahead and take the derivative. We get 21 minus 2x, and we're going to get that x equals 10.5. So 10.5 times 10.5, that will be our product. And we're going to get a product of 110.25. That's our maximum product. And then x is 10.5 and y is 10.5. The idea is like, they're kind of talking about squares when we're talking about product that's just going to be x times y. And if we want to maximize the area of a rectangle, we always get a square. That's why our x's and y's are continuously being the same number. So let's take a look at number 3 now. They say find two numbers whose difference is 15 and whose product is a minimum. So we're saying a difference. So x minus y equals 15, and we're trying to minimize x times y. So if I solve for y, or actually I think I'm going to solve for x in this problem, I get x equals 15 plus y, which means that I am going to minimize 15 plus y times y, which means that I'm trying to minimize 15y plus y squared. So in order to do that, I'm going to take the derivative. I'll get 15 plus 2y, and setting that equal to 0. So if I move the 15 over, I'll get 2y equals negative 15, so y is negative 7.5. So y is negative 7.5, which means that x is positive 7.5. The difference between 7.5 and negative 7.5 is 15. So what is our product going to be? It'd be 7.5 times negative 7.5, which gives us negative 56.25. This is our product. Number 4, they're asking find two numbers whose difference is 21 and whose product is a minimum. All right, so x minus y equals 21, which means that x is 21 plus y. We're trying to minimize x times y, which means that we're trying to minimize 21 plus y times y, which would be minimizing 21y plus y squared. So we're going to take its derivative. We get 21, just 21, plus 2y, and we're setting that equal to 0. And we're going to get that y is negative 10.5. That gives us that x is positive 10.5. And our product will be 10.5 times negative 10.5, which gives us a product of negative 110.25. Okay, so number 15, it says, or not number 15, number 5, it says find two positive numbers whose product is 15 and whose sum is a minimum. So two numbers that multiply to be 15, x times y equals 15. And they say the product is a minimum. So we're trying to minimize, or whose sum is a minimum. So we're trying to minimize x plus y. So I need to solve one of these variables. It doesn't matter if I go for x or if I go for y. So I'll say that y is 15 over x. So let's plug that in over here where we're minimizing. So we're trying to minimize x plus 15 over x, which really means that we're trying to minimize x plus 15x to the negative 1. So I need to take the derivative. The derivative of x is 1. The derivative of 15x to the negative 1 is going to be minus 15x to the negative 2. Set that equal to 0. This is really 1 minus 15 over x squared equals 0. So I can say that 1 equals 15 over x squared. Multiply both sides by x squared, and I will get that x squared equals 15. Take the square root, and this should give me a plus or minus. What is the square root of 15? Square root 15. We're going to get like 3.87. And this is plus or minus, but they said two positive numbers, so I've got to go with the positive. I'm going to get x equals 3.87, which will also mean that y is 3.87. So some closing thoughts on this section. Optimization is probably one of the more challenging sections to get started. It really uses all of our calc knowledge, because so far our examples, we've just had to use power rules, but in theory we could have quotients, products, chains, logarithmic functions. I mean, we could have it all. So usually what people struggle with the most is just getting started. The calculus itself tends to be okay, but trying to come up with a relationship of how the variables connect to each other is a challenge in itself, and it takes lots and lots of practice. So if you're not getting it right away, don't feel bad. This is probably the hardest section that we've done yet. It's also the last section that we're going to do before break, because after this we're going to start talking about antiderivatives and integrals, which if you remember back from the beginning of the year, I said calculus can really be broken into 3 parts: limits, derivatives, and integrals. We're approaching integrals. So don't worry about integrals yet, because that's going to be the next chapter. So for right now, just practice these problems. If you get stuck, feel free to reach out. The homework and the notes will be posted on Classroom. So yeah, if you got questions, just let me know.